Okay, good morning, guys. Welcome to the first online lesson that we're going to have. Um, I've already made one of these videos for another class, and so I'm hoping that I've got this pretty much down. But again, just please keep in mind that this is definitely still new to me, a little new to you, I suppose. And so trying to get through it with little mistakes and as quickly as efficiently as possible. Here's how I'm just going to try and do this, at least for now. And again, I welcome your feedback in terms of what could be better or, what's working, what's not working. So please make sure you let me know that. I've got a couple of slides that I'm going to go through, and I'm going to basically center the instruction around these slides. Some of them will go much faster than others. And so I'm hoping to, like I said, sort of get through it as efficiently as I can. What I would like you to do is definitely have out a notebook and something to write with. All right. And then also have that shared Google Doc out. And I will be there with you. I'm actually there with you right now in real time, answering any questions that you might have, looking at any comments you might have. And again, I'll try and answer those right away through that Google Doc. You can pause this video at any point in time, put a question in there, and look at my answer when I get to you. And so that's sort of, I think, our main mode of communication. If you think you need something a little bit better than that, a little deeper, we can certainly do sort of a one-on-one chat or even a video chat if we really want to. Just email me and let me know, or type it into the Google Doc, and we can definitely set that up. All right. So again, let's try and get through this the best that we can. Let me know what questions you might have, and we'll go from there. All right. So let's jump into it. I want to just start off by, here's sort of my goals. This is actually goals for the rest of the unit. So this is sort of everything that we'll do for kind of the rest of the year. Really, this will kind of round out the Power Series unit. We're not going to get through everything, certainly in this video. I'm hoping by the time we get to some of this stuff down here, we'll be back together in person. That's my hope, right? But we are definitely going to look at the first two bullets today. And so really what we want to do, and this will be a quick one, this first one will be quick, use Taylor polynomials to approximate values of known functions. So we've worked on creating Taylor polynomials, what we did in last class, what you did for homework. Can we use those polynomials to approximate values of functions that we already know? And I'll explain sort of how that looks and why we might take that step right now. It's going to come up in the future a little bit more, but for right now, just kind of want to show you, hey, this is what it looks like. This is how it relates to the function, so on and so forth. The big goal for today is to use the ratio test to identify an interval of convergence. So we've actually talked about that a little bit, and I'll get into that. And then this idea of a radius of convergence for a power series. Both very similar. They're connected, absolutely. And I just want to kind of go through these steps. Okay, so this becomes a really big part of everything that we do moving forward. You will almost absolutely, and I'm going to take out the almost, you will absolutely have to do this on the AP exam. So kind of put my AP hat on. This is a huge part of what you'll do for the AP exam, whether it's a multiple choice question or a free response question. So this is kind of a big lesson in terms of how to do that. All right. The next three, eventually, we'll get to these. So we'll eventually start talking about general Taylor and Maclaurin series. I'll get into, what these guys are. We talked about Taylor polynomials for these four big functions. So eventually we're actually going to want to know the general Taylor series for sine x cosine e to the x and 1 over 1 minus x, sort of right off the bat without having to construct them every time like we did before. We'll talk about, what those look like. Eventually we'll be able to add, subtract, multiply, divide. We'll do composition, differentiate, and integrate power series of known functions. So something like sine of x squared, we talked about that, right? Or cosine of e to the x. What does that function look like, and how would we take its integral? We'll also do, what happens if we want to add or subtract a power series? How does that work? What happens when you multiply? And this will all be working with polynomials as well. Again, that's to come. And then finally, the last thing we usually do is find the error bound, which is called the Lagrange error bound. So Lagrange, another famous mathematician. this goes back to sort of this first bullet. So we'll come back to this eventually of, well, what is the difference between, or what's the error that we can find for approximating values of known functions and using a Taylor polynomial? Again, that'll be sort of the last thing we do. So we'll come back to that. All right. All right, let's keep moving here. So I want to talk about just sort of what we've done already. And what we've done already is we've created a Taylor polynomial, right? This is the general form of how you create a Taylor polynomial. Hopefully you recognize this from our notes from last class. If you don't, certainly recommend that you pause the video at this point, go back to those notes from our very last class last week, and look at, well, how did this come about? Where does this come into play? Biggest difference between our notes and this formula that's on the screen right now is that we used a C for the center instead of A. So that would be f to the n of c over n factorial x minus c to the nth instead of the a's there for us. And I'll use c's pretty much throughout the rest of this video, but this was just something I captured that was already nice and formatted. So these are c's, those are the centers, right? And we kind of made out this whole thing. And again, this is how we created the sine Taylor polynomial. And so this is what it looked like, right? So we went to, I don't think we went all the way to the 9th degree, but I believe we used a 5th degree Taylor polynomial. This is what the 7th and the 9th degree Taylor polynomial for sine of x look like. If you were to carry out the derivatives to the 9th derivative to the 7th derivative and sort of put all the together, this is what those polynomials would look like. And so you see, you can just keep getting farther and further and further. You could go to the 11th degree, the 13th degree. Hopefully you see the pattern here that there's actually no even values or even powers of x because their derivatives are 0. So they just go away. And so this is just sort of a look at, well, this is what the Taylor polynomial was. This is how it was formed. And then finally, this is how the graphical representation looks. Right. So here is this 1st degree Taylor polynomial sine mapped onto the actual sine function. And then we just keep getting further and further along. All right. So the higher the degree of the Taylor polynomial, this last one is a 9th degree Taylor polynomial. And you can see that it really starts to see that sine curve come out. Right. It eventually pulls away from it right down here and up here. But for a lot more of x than we did, all the way back here, it follows the curve exactly. And that's this polynomial. Okay, so it follows the curve pretty closely. All right. What you did for homework, and if you haven't done so already, I've posted the solutions, excuse me, for this on my Malvern. So please make sure you go and check that out. How did we get to these Taylor polynomials? This is the 6th degree Taylor polynomial for cosine. This is the 4th degree Taylor polynomial for e to the x. If you're not sure where these numbers are coming from or where this is coming from, please, again, pause the video right now, go to my Malvern under topics, under power series, and you'll see pictures of these 2 solutions out. If you have questions on those, again, Google Doc, please put those in there. Or send me an email or do something to make sure that we're getting your questions answered. Okay. And I can try and answer you directly or give you a little bit of guidance on that. So just wanted to show you this. This is exactly how we did it in class, just with cosine and e to the x. And hopefully you were successful with this. All right. And again, if not, let me know if you have any questions. So this is the first bullet that I talked about in the goals. This will go really pretty quickly, actually, for us today. And so I don't want to focus a whole lot on this. I just wanted to show you this because this will set up, like I said, that last part of using the error bound eventually. And so this will be more useful when we're sort of doing integration of known functions where it's not possible unless you turn it into a series representation. So we're just kind of hanging, just getting the hang of it for now in terms of, well, how could it be used and what does it mean? And so I just want to show you a really quick example for, could I approximate the value of f of 2 for f of x equals e to the x, right? And so really what I'm doing is, if I didn't have a calculator, right? If I didn't have some way of knowing what e to the second actually was in decimal form, could I approximate it? And the answer is yes, right? I could change e to the x or turn it into a power series, get a Taylor polynomial, a representation of e to the x using a polynomial. And so I'm going to use the one we did for homework, just kind of for continuity there. And so we learned that e to the x is approximately equal to this fourth degree polynomial, which means that I can replace this x with any number. And as soon as I replace this x, let's say with 2, I just substitute that same value in for these x's. Boom, boom, boom. So 1 plus 2 to the second over second, so on and so forth. And I would end up getting, after I simplify all this down to here, 1 plus 2 plus 2 plus 4 thirds plus 2 thirds, that actually just equals 7, which is a nice number, and it's much easier to find than actually trying to do e to the second, right? So 2.7, whatever, all squared. It is approximately equal to 7. And so we know that e to the second is not actually just 7. That would be too nice and too easy. But actually, this is pretty darn close. So here is the actual value of e to the second. So 7.389, so on and so forth. And you could do that in your calculator if you wanted to. Again, I know that that's not exact, but for using a polynomial to the fourth degree, that's really close, right? I'm only about 4/10 off of the actual value for e to the second using this polynomial. And so there is some error associated with this, which again, we'll talk about sort of at the very end, but I just wanted to show you this for right now, that if I plug in 2 for my Taylor polynomial for e to the x, I can get all the way to 7. And I know that e to the second is approximately equal to 7, which again, we were pretty darn close. So I think that's pretty cool, where you can take a function that's not easy to work with, which is e to the x, because it's an irrational decimal, and get really close to the answer just by using this Taylor polynomial. So e to the second, that's what it is actually equal to. This is what it's approximately equal to using a Taylor polynomial. So that's how we can use Taylor polynomials to approximate outputs of known functions. Just a quick example. Okay, so here's what I really want to get into today. This is the main part of today's lesson. It's talking about the interval and radius of convergence. So we've actually already talked about interval of convergence a little bit. We've already found an interval of convergence, which this is a recap of that first example we did in class. And so the big new part here is this radius of convergence. So there's some new terminology there. What does it mean to have a radius of convergence? And how would I find that? The good news is that you're actually going to go through the same steps you would for the interval of convergence. And so these two things are highly linked together. It's just a matter of, hey, this is the interval, this is the radius. What's the difference between the two? How do I find one versus the other? Okay, so that's really what today's lesson is going to be about. Before I move forward, again, I just want to say, when we're talking about convergence for power series, it's different than convergence for infinite series, right? The convergence for infinite series meant that summation, that infinite summation, settled on some real value, right? So it converged to some real number at some point in time, as n got really, really large. For convergence with power series, it's much more closely linked to, for what values of x does this power series converge to a function, right? What function is this related to? And so if I go back up to this slide with sine of x, I know that, well, depending on how far I go out with these Taylor polynomials, right? Let's say I went to infinity. So take this 9th degree Taylor polynomial, but keep adding x to the 11th over 11 factorial, x to the 13th over 13 factorial, all the way to x to the infinity over infinity factorial. Bad math there, but just to get you the idea, right? I could take this all the way out to infinity. And what we see is that if we did that, then since this keeps getting closer and closer to the actual sine curve, the interval of convergence for sine x is actually going to be infinity. I can plug any number in for x for sine, and if I plug it into the infinite Taylor polynomial for sine of x, they would equal the exact same thing. So the convergence of sine's power series is infinite. X, the interval of convergence is infinite. I can plug any value in for the power series for sine, and I get the exact same output as if I were actually plugging into the sine function. So convergence for power series, talking about converging to the outputs of a function as x changes, right? I want the outputs of the power series to equal the exact outputs of the function that I'm trying to map to. All right. Just to give you a little bit of a preview there as to sort of what's to come and I think the higher meaning of this convergence pieces. All right. So here's the example we did in class a little bit. And I just want to go over it again just to make sure. I won't go through too in depth, but this will set up everything that we do for the rest of today. So here was the power series that we used. Just kind of a random power series that I put together just to show you how we can get to the interval of convergence. X to the n over -4 to the n times n itself. First thing we always did was use the ratio test. So ratio test is a really powerful tool for us. It sets up an inequality at the end where I know that this limit as n goes to infinity needs to be less than 1 in order for the series to converge, right? And so since this comes out to the absolute value of x over 4, I know that this needs to be less than 1, right, in order for this to converge. And how do we take care of that? Well, we said, all right, well, if the absolute value of x is over 4 is less than 1, I could multiply both sides by 4. So I get the absolute value of x. And I apologize. This digital pen is kind of, it's not very clean. So it's a little hard to use. So I'm not going to use a whole lot, but at certain points I will use it. So apologies if this gets a little messy. I'll erase if I have to. Absolute value of x is less than 4. And then we set up a double inequality, which looks like this, right? Where -1 was less than x. I'm sorry. I'm going to go back. I'm going to erase this, right? We set up a double inequality where we had -4 is less than x, which is less than +4, right? So those two things are the same. This and this are the same, okay? And then the very last thing we did was we checked our endpoints. How do we check our endpoints? Again, if you're confused by that or not sure about that, highly recommend that you go back to your notes and check out that process. But basically what we did was we took -4, we plugged it in for x into the original series. Once I get rid of the x, it's no longer a power series, just an infinite series. I simplified that infinite series and used my infinite series test from what we learned before. And I found out that that series was divergent. Hence, there's no equal to sign here, right? It's just less than. And then I plugged in +4 into this power series. Once I get rid of the x, no longer power series, an infinite series. It turned out to simplify all the way down to the alternating harmonic series, which I know is convergent. Therefore, this is a convergent piece, and that's why it's a less than or equal to at 4. All right, so that's just, again, a recap of what we did with that one. That was an interval of convergence. So we actually found the interval of convergence for that one. So you've already got that piece of notes in there. All right. Wanted to look at just a couple more. And then really start to get into the new thing, which is the radius of convergence. Now, the good thing is that the radius of convergence actually comes out while you're finding the interval of convergence. So again, the most amount of work that you'll ever have to do is this, going through these steps, finding this interval of convergence, okay? Because if you find the interval of convergence, you actually already know the radius of convergence. So we're going to talk about that. So a couple of things we know. We know that power series are based around a center value, right? There's that x minus c part. The only center we've used so far to construct power series was 0. You can use any number you want. Right? You could use 2, you could use -2, you could use 1/2, you could use -4/3, doesn't matter. All right. You actually, you're able to pick, well, where do I want to start centering this power series? And so we see that this x minus c term is in that general power series formation. All right. So there's some center value that I'm going to use. The basics of what a radius of convergence means is how far away from that center value on both sides. So both the left of the center value and to the right of the center value does the power series converge. And so what ends up happening, which is kind of neat, and it's because of this absolute value inequality, which turns into a double inequality, is that, well, it's actually equal distance on both sides. So if you've got some center value C, the interval that that power series converges for is going to be equidistant from the center to the left and from the center to the right. And we'll get into exactly, I think, a little bit more of what that means and how that finds or how that's found. But it's really just, hey, I have a center value. I know that the power series converges for X values, 3 units to the left of that center and 3 units to the right of that center. And so your radius would be 3 in that case. And so we'll get into that a little bit. The good news, and this is what I was saying about you're actually already doing this at one point through the interval of convergence, is that every ratio test will eventually simplify to this form, right? I've got this X minus C, the absolute value. It's always going to be less than some number. And so if I go back to this one, I had the absolute value of X is less than 4, which is the absolute value of X minus 0 is less than 4 because the center here is 0. And so we actually saw this already. Whenever I get to this point, and it has to look exactly like this, X minus C, not some number times X minus C, but just X minus C is less than some real number R. That is my radius. So again, you'll see this come through. We've actually already done it. We just haven't called it the radius. All right. And R is in fact the radius of convergence. All right. So let's take a look at one. Let's go through an example. I think that'll help. So here's an example of a power series. How do I know it's a power series? Well, there's an X in there. There's an extra variable. And then I've also got my N power, which is what I'll be plugging these numbers in for. N equals 0, 1, 2, 3, 4, so on and so forth. And so I'm going to start off by using the ratio test. That's going to be my first steps for both of these types of questions, finding the interval of convergence or finding the radius of convergence. And so I set up my ratio test, changing all my n's to n plus 1. So there's only this 1 up here, and then dividing that by the original series. So 3 times x minus 2 to the nth. I simplify the inside of the absolute value as much as I can. And this one simplifies really nicely, right? The 3's cancel, n plus 1 over n. I'm just going to subtract those exponents because they have a common base of x minus 2. And so it really just becomes x minus 2 to the first. And so this whole thing actually just boils down to the absolute value of x minus 2. What's interesting here is that, and this does not happen every time, is when I get through my first steps of my ratio test, there actually aren't any n's left. There's no other n except for the exponent in this example. And so there's no n to actually take to infinity. And so I'm going to get rid of my limit at that point because there are no n's, okay? So I just have the absolute value of x minus 2. I know that the ratio test shows convergence when its result of the limit, so whatever's left after the limit, is less than 1. And so the absolute value of x minus 2 has to be less than 1 in order for this power series to converge. And again, we're looking for the x values in which this converges for. But really what I'm talking about right now is the radius of convergence. And so I've got this absolute value of x minus 2 is less than 1. And I had told you from the previous slide up there that as soon as I get to this part, the absolute value of x minus c, so you see that my center value is 2 in this case, is less than r, this value will be the radius of convergence. And so in this case, I'll go back to this slide really quickly, took the ratio test, simplified to absolute value of x minus 2. I set that less than 1 in order to find what values of x actually cause this to be less than 1. But before I do that, I stop right here because this tells me, nicely enough, the radius of convergence, which is 1. And so that's why I have here, the radius of convergence is equal to 1. I know that I can take this guy, turn it into a double inequality, right? Greater than -1, less than +1. And I can solve for x by adding 2 to both sides. And this is where I get my interval of convergence. So actually, you can do it for yourself. You can plug in 1 and 3 into the original power series at this point and try and figure out, well, why is it, less than and less than. I think I'd get to that a little bit later on, but if not, you can definitely try that yourself and try and simplify that power series and see why they both diverge. Okay, so this is the finish of example one. Just want to, again, why are we saying it's a radius of convergence? What does that even mean? This is a really nice form, and if I get to this, that R is really easy to pick out. But what is it? What am I actually saying? What am I actually talking about? Again, we are centering this power series around 2. So I'm building this function, this infinite polynomial, around 2, which means I'm going to start at 2 and go to the right, and then I'm going to start at 2 and go to the left, whatever that polynomial looks like. But what does it actually converge? Why does it, what values of x actually converge to a known function? And so I know that the radius is equal to 1. And you can kind of see that, right? So if I'm centering at 2, x is equal to 2. And so if it converges for x less than 1 and x greater than 1 and x less than 3, then it's really one value away from the 2 on both the left and the right, right? So this distance is 1 unit. This distance, sorry, again, this pen, not great, is 1 unit. Okay, so I have this radius, think of it like this being the center of the circle, and you draw a circle out, its radius would be 1 unit, right? So if 2 is the center of the circle, radius of 1 would capture all of these x values in between 1 and 2, and then 2 and 3. And those would be the values that actually converge for this power series. So this radius example idea is that, hey, I'm starting at 2, I'm going to the left 1 unit and going to the right 1 unit. All the x values that I pick up along the way converge. They cause the original power series to converge, which is nice. It's good. Okay, so that's my radius of convergence. Here. Put it on the slide. There we go. So here's my second example. This one's a little bit more involved, okay? At this point, I have the whole ratio test listed out here. Definitely encourage you to pause the video if you need to. Just kind of work through yourself where all these steps are coming from, where all the n+1s are coming from, how the simplification happens, so on and so forth, okay? And so again, pause the video if you need to. I'm going to talk about it just a little bit here, but certainly pause it if you need to work through it yourself. So I've got this power series 2 to the n over n times 4x minus 8 to the n. I know it's power series because there's an x and there's an n. Okay, we're good there. So if I'm finding the radius and the interval of convergence, I'm starting at the same spot for both of them, which is the ratio test. So I'll set up the limit as n goes to infinity. I'll replace all my n's with n+1s, and then I'll multiply by the reciprocal of the original power series, which is right here. I'll work my way to simplifying as much as I can. So 2 to the n+1 over 2 to the n just gets simplified to 2. That's where that 2 comes from. I've got 4x minus 8 to the n+1 over 4x minus 8 just to the nth. Those exponents would subtract from one another. n+1 minus n, just 4x minus 8 to the positive 1. So I have 4x minus 8 on top. And then the n and the n+1, they don't do anything. They just stay as n and n+1. So n and n+1 down here. Okay. All right. So now I don't get as lucky because there are n's still in here. So I can't just jump right to my absolute value inequality. I have to do a little bit more work. And so the limit as n goes to infinity. This is n to the first over n to the first. I know that, if you want to think of those horizontal asymptote rules or just limit rules in general, since these two are the same power, n to the first and n to the first, I'm just going to be left with everything else, basically, right? So nothing's going to go away. It's not going to go to 0 or infinity. I'm actually going to be left with the other pieces still in the limit. And so what's left over is the 4x minus 8 is definitely going to be left over. And in fact, since there are no n's attached to 4x minus 8, just like a constant, I could pull that out in front of the limit. That's why you'll see this absolute value of 4x minus 8 come all the way out in front. And then what's left over is 2n over n+1. This is a nice, easy limit for us to do. I know that that's just going to be equal to 2. All right. And so in the end, the ratio test shows me that this limit as n goes to infinity is equal to 2 times the absolute value of 4x minus 8. Very important to keep the 4x minus 8 in absolute value because that's the actual piece that could change because I can plug any number in for x. I can't plug any number in for n. It's all positive numbers, right? But I can plug any number, whether it's positive or negative, in for x. So it needs to stay in the absolute value. Okay, so once I've got my result of that ratio test, I'm going to set it, less than 1, create this inequality. So I run into a little bit of a problem here. It's not as nice, right? What I see is that I really need this absolute value of x minus c is less than r exactly. Okay. I don't want a number in front of the x. I don't want anything on the outside here. And so I have to do a little bit more work. Number one, I got to get rid of this 2, and I also have to get rid of this 4, right? So what we can do is we can actually factor a 4 from this absolute value. If I factor a positive 4, it's fine, right? It doesn't change it because it is positive. So I can factor a 4 out of an absolute value, no problem. And once I do that, so I factor a 4 from the absolute value, bring it out, 4 times 2 is 8. I get 8 times the absolute value of x minus 2 is less than 1. This is really nice, right? Because it's really close to this x minus c is less than r. I've gotten rid of the coefficient from the x. And so now I just need to solve for the right side of the inequality. I can divide both sides by 8, and I get the absolute value of x minus 2 is less than 1/8. That's this form exactly right here, right? X minus c is less than r. X minus 2 is less than 1/8. 1/8 is my radius of convergence right there. Very good. Okay. And then if I want to find my interval of convergence, again, I would set up my double inequality. X minus 2 is less than positive 1/8, but it's greater than negative 1/8. And then I would add 2 to both sides of that double inequality, and I would eventually get here. Okay. So I have a couple things here already, and I'm going to go through it. Not completely, but I have slides that you can pause on if you want to work through it yourself and just kind of understand. But the interval of convergence here actually ends up being this is greater than or equal to, and this is just a less than. All right, so it converges for 15/8, but not for 17/8. Kind of a small interval there, but that's how that one works out. Okay. So last step, this is sort of the finish for this one. Again, we actually already did this already. We talked about this already, so I'm not going to go through in depth, but definitely worth talking about still and just reiterating because you're going to have to do this on your own. Is once we get to this double inequality, again, let's say that we didn't know whether this was less than or equal to, or this was just less than. I have to check what happens at 15/8, and I have to check what happens at 17/8. I'm going to substitute both of those separately, right, into the original series for x. So not for n, just for x, right? So the only play would be 4 times 15/8, see what happens there, and then 4 times 17/8, and simplify this, all right? So here's what they look like. Again, pause the video if you need to work through this on your own, or just take a couple more minutes on it. When I plug in x equals 15/8, this is what it simplifies all the way to, all right? And this one's really nice because it simplifies all the way down to the alternating harmonic series, which I know converges, which is why you see, if I go back one slide, that's why this is less than or equal to, because at 15/8, it actually does converge. Okay, so again, pause it if you need to work through why all that happens. Let me know if you have questions. And then, I'm sorry, I thought I put the 17/8 on here as well. I guess I would encourage you to put try the 17/8, right? So actually plug in 17/8 into this original series and see why it diverges instead of converges. I'll send you that note in a separate email here. Okay. Apologies about that. I thought I put that slide in because I didn't. Okay. So that's just the general idea of what a radius of convergence is. 2 examples of how to find a radius of convergence. There are 3 possibilities for the radius and interval of convergence. So there's really only 3 big general ideas or general answers that you can get when talking about the radius of convergence and the interval of convergence. So I want to go through all 3 of them so you understand what happens if the radius of convergence or the ratio test comes out to be infinity before I can even get to the inequality? Or what happens when the ratio test equals 0 before I can even get to the inequality? And so that's part of these possibilities. I'm going to talk about, well, how can you interpret that when it happens, and what should your answer look like when that happens? Okay, so first thing is, what happens when the initial ratio test goes to infinity? So I don't get a number, or the absolute value is not even there anymore because the ratio test goes to infinity. And so let's talk about that one a little bit. Here's an example. I've got the power series, n factorial 2x plus 1 to the nth. Same first step, set up your ratio test. Okay, so this is what the ratio test setup would look like for this power series. I would do as much simplification as I possibly can with this. So they're just taking this step, n plus 1 factorial is equal to n plus 1 over n factorial. So the n factorials are the only things that actually cancel completely. The 2x plus 1 and the n plus 1 over 2x plus n just goes to 2x plus 1 to the first on top. And so that whole thing, again, taking the 2x plus 1 out of the limit because it has no n's attached to it, is equal to the limit as n goes to infinity of n plus 1, which we know is infinity. Right, so think about this for a second. Ratio test says that the series converges when the ratio test limit is less than 1. Well, if we get infinity out of the ratio test at any point in time, we know that infinity is definitely not less than 1, right? So what does it tell us? Well, it basically tells me that the power series does not converge for almost every value of x. Okay, so this power series does not converge pretty much ever. The only x value in which this power series would converge is the center value. So what is the center of this power series? Where did it start? And the answer to that is actually it's negative 1/2. All right. And so if you wanted to figure out, well, why is it negative 1/2? Why is the center here negative 1/2 for this power series? You can take this inside part, this, whatever 2x plus 1, and the other one we saw was a 4x plus 8. And you can set that equal to 1 and solve for x. And when you do that, set it equal to 0. Set it equal to 0 and solve for x. So 2x plus 1 is equal to 0, solve for x. That's your center value. All right, because again, you're starting on the x-axis and building a polynomial from there. And so I need to find where is the center on the x-axis that this whole thing is built off of. All right, so center for this one, c equals negative 1/2, 2x plus 1 equals 0, subtract 1, divide by 2, x equals negative 1/2. That's where I start. So now, since my ratio test showed that the limit as n goes to infinity of that ratio test is infinity, I know that infinity is definitely not less than 1. Therefore, the only value of x that this series converges for is its center. Why does that happen? Well, when I plug in the center value, negative 1/2, into this infinite series, so 2 times negative 1/2 plus 1, this goes to 0, which means every term goes to 0. And so that's a convergent number, 0, right? And so the infinite sum of just 0 itself is always going to be 0, which converges. And so this only works when x is equal to its center value, or in this case, negative 1/2. All right. For all other x values, the series diverges, which means it does not have an interval of convergence, right? Because you can't go any further out than the center value. So there's no interval to even calculate or to look at. The radius of convergence is also just 0. There's no radius at all. I'm not building anything. I'm not going left or right for any value. I'm just staying at negative 1/2. And so the radius of convergence is 0. All right. So in total, when you have a ratio test for a power series that finishes with infinity, right? So the limit does not exist. Your interval of convergence does not exist. There is no interval of convergence, and the radius of convergence is always equal to 0. Right? Those are the things you definitely want to write down in terms of big notes and big outcomes. Okay, trying to get through here. So the second possibility is, well, what happens if the initial ratio test goes to 0? What does that mean? How can that be interpreted? So again, let's take a look at an example and then talk about the result. So this is a power series, x to the nth over n factorial. Quick side note, this is actually the general power series for e to the x. So this series represents e to the x as a power series, as an infinite polynomial. So first step, set up your ratio test. X to the n plus 1 over n plus 1 factorial multiplied by the reciprocal of the original power series n factorial over x to the nth. Simplify the inside as much as you can. You get to the limit as n goes to infinity of x over n plus 1. Right, so x to the n plus 1 over x to the n, just x to the first, and then n plus 1 factorial times n factorial on top is just n plus 1 on the bottom. Again, I'm only plugging in values for this limit for n at this point. And so I know that there's no n in the numerator, only an n in the denominator, which means that this limit is going to go to 0 because the denominator is going to grow infinitely large while the top stays the same. So now the ratio test for this power series goes to 0. The limit does. Well, what does that mean? And how can I use that to my advantage? Well, what I know is that in this case, 0 is always less than 1, right? So it doesn't matter what value of x I would plug in for this limit, right? Pick any value for x, doesn't matter. The limit will always equal 0, right? And since 0 is always less than 1, this is really nice because now I know that the power series converges for all values of x. There's no value of x that I can't choose that this series, this infinite polynomial, does not converge to e to the x. The outputs of this infinite polynomial will equal the outputs of e to the x for every single value of x that you choose. All right. Its interval of convergence is negative infinity to infinity, and its radius of convergence is positive infinity. Pretty cool. Okay. So those are the two big new ones, right? What happens when the ratio test goes to infinity? What happens when the ratio test goes to 0? The answers are actually really quick, which is nice, and you don't have to do a whole lot of extra work. So those are the ones that are really nice to come by. I hope that you understand sort of the outcomes. Again, if you don't, please make sure you're writing a question down or a clarification, and I can try and help you out as much as I can. Okay, so the third one, I don't really have a lot here to do because, well, you've already done this. We've already done a couple of different examples throughout this video, and we did one in class. Is when the initial ratio test does not equal infinity or 0, but any other real number, right? So we saw that in the very first example that we did in class. We saw that through 2 examples in this video. We want to go through the steps from the first example in class and the first 2 examples in this video. I'm repeating myself, and figure out what the radius is, right? And so if I were to go back, that would be something like this example 1, right? The ratio test did not come to 0 infinity. It came to the absolute value of x minus 2. Okay, and then I actually had to solve for the radius of convergence at that point. For interval of convergence, let's take this one, right? So here's my ratio test, does not go to 0 or infinity. In order to find the interval of convergence, I needed to check out what was happening with the endpoints, plug them back into the original series, do individual convergence or divergence tests for that, and come up with a final interval of convergence. Okay, so the third possibility is basically the examples that we've already done. All right. Oh, look, and I'm just finding this other slide that I wanted all the way back at the top. So this was that endpoint 17/8 for example number 2, all the way up there. So if you want to go back and check out, well, here's what happens when 17/8 is plugged into that power series, and it ends up being just the harmonic series, and that's why we know it diverges. All right, sorry, sidetrack. Back to number 3. Go through the steps from the first 2 examples. Again, that's what you'll have to do. Not every time, but I think that comes up more often than not, that you have to go through those steps. All right, I'm done talking. I hope this was helpful. Again, first crack at this for me and for you. So please let me know what I can do to help you out as much as I can moving forward here. Here's your homework that's going to be due at the start of tomorrow's class, right, which is 12:55. Okay, so this is due at 12:55. Please send a picture of your work by that time. Using your textbooks. And again, your textbook's actually really nice. I actually think the textbook does a nice job with these sections. So use that as an extra resource. What you'll be having to do here is really just finding radius and interval convergence throughout these. All right. So you'll see a couple of different examples of all the possibilities that we went through. And so I'm hoping that you have some success with that. If not, let me know. Use the Google Doc, email me, whatever it might be. Those solutions will be posted in my Malvern as usual under topics, under Power Series. You'll see the pictures there. All right, I'm done. Have a great day, guys. I hope this was helpful, and I'll talk to you soon.